Ohm's law, which states that current is equal to voltage divided by resistance. In a DC circuit, voltage and resistance are the only factors that affect the amount of current flow. An AC circuit, however, is a bit more complicated. Current flow through an AC circuit is affected by voltage and resistance, just like a DC circuit. But in an AC circuit, current flow is also affected by two other factors, inductance and capacitance. We'll be talking about inductance in this segment, and we'll cover capacitance in the next segment. The effects of inductance on current flow are especially evident in an AC motor. We're going to follow an electrician through the proper procedures for measuring the resistance of this AC motor. We'll then use Ohm's law to figure the predicted current flowing through the motor. Our electrician will then measure the actual current of the motor. You may be surprised at the difference between predicted and actual current in this motor. To check the resistance of this motor, the electrician is going to measure resistance at the motor controller. The first and most important step in this procedure is making sure that the motor has been tagged out. Once this is done, the cover of the motor controller can be removed. With the cover removed, the electrician checks to make sure the motor has been de-energized. He does this by checking to see if there's any voltage coming into the controller. He does this by checking the voltage across each of the three wires, then checking voltage to ground from each of the three wires. The voltage reads 0 on all checks, so the electrician can be certain that the motor has been de-energized. The next step in checking resistance is to switch the meter to the resistance scale, zero it, and then check the motor. The proper procedure for this is to check each of the three windings. Let's see, the first one reads about 0.3 ohms. The second one about the same, and the third one again 0.3 ohms. We know that the voltage that's applied to the motor when it's running is 480 volts. So we have the values we need to calculate current. According to Ohm's law, I equals E over R. Current equals 480 volts divided by 0.3 ohms. So I equals 1,600 amps. And 1,600 amps is a lot of current. But that's what the current would be if it only had resistance to limit it. Now let's get an actual current measurement and see how close the predicted value is to the actual value. The red tag has been removed from the motor and it is now running normally. Our electrician is going to use a standard clamp-on ammeter to measure current flow in the motor. Notice that he has followed safe working procedures by isolating his work area from the rest of the plant with barricades. He carefully removes the cover from the motor controller and sets it out of the way. Finally, he lays out the equipment he will need to make the test. The leather-covered rubber safety gloves are used for protection. With the gloves on and the ammeter ready, the test can begin. When the ammeter is clamped to the first wire, it reads about 42 amps. The second wire also reads 42 amps, and the third wire reads about 42 amps. It's obvious that something else besides resistance is limiting current flow. That something else is inductance. Inductance is a physical property of all AC circuits that opposes any change in current flow. Inductance is important because, as we just saw with the motor, it can have a major role in determining how much current a piece of equipment draws. When we talk about the effects of inductance, we generally use another term, inductive reactance. Inductance, as I said, is a physical property of all AC circuits. Inductive reactance is the measure of the opposition to current flow that's created by inductance. Because inductive reactance opposes current flow, it, like resistance, is measured in ohms. Now, let's look at just how inductive reactance limits current flow. Current flow is actually limited by an induced voltage that opposes the applied voltage. This induced voltage is called counter voltage, or more commonly, counter electromotive force, CEMF. CEMF is caused by self-induction. That is, the induction of voltage in a wire by AC current flowing through that wire. This cross-sectional view of a wire can help us understand how self-induction works. When voltage is applied to the wire, current starts flowing through it. Since we're looking at the end of the wire, the direction of current flow is straight at us as soon as the voltage is applied. The magnetic field that builds up starts at the center of the wire and moves outward. At this point, all the magnetic lines of flux are still inside the wire. An instant later, the field is still building up. There are more magnetic lines now, and some of them have expanded around the outside of the wire. Each one of these lines started at the center of the wire and cut through all or part of the wire to reach its present position. Another instant later, the magnetic field has still more lines, and most of the lines have cut through the wire. The magnetic field will not build up any further because the current that's producing it has reached its peak positive value. Let's stop here for a minute and review what has happened. What we just saw was a conductor in a changing magnetic field. With a conductor, a magnetic field, and relative motion, we get voltage. In this case, a current-carrying conductor induced a voltage in itself, so we call the process self-induction. As the magnetic field moved outward, the voltage induced in the conductor was opposite in polarity to the applied voltage. This opposite voltage is the CEMF. Because it opposes the applied voltage, the CEMF limits current. Now, let's see what happens during the next part of the AC cycle. After current reaches its peak positive value, it decreases until it reaches zero. You remember that from the sine wave we looked at earlier. As current decreases, the magnetic field collapses. The motion of the magnetic field collapsing is opposite to the motion of the field building up. Since the motion is opposite, the self-induction is also opposite. The voltage that's induced in the conductor now has the same polarity as the applied voltage. When the magnetic field has collapsed completely, there is no motion, so there is no self-induction. As current starts to increase toward its peak negative value, the magnetic field builds up again. Whenever there's a variation in current, the magnetic field also varies. As the magnetic lines of flux move, they cut across the current-carrying conductor. The voltage that's induced in the conductor is always in such a direction as to oppose the current change. In other words, if current is trying to increase, the induced voltage opposes the applied voltage, and if current is trying to decrease, the induced voltage aids the applied voltage. The number of magnetic lines of flux that cut across a conductor is important because it affects the inductive reactance in a circuit. That is, the amount that current flow is limited. Anything that increases the number of magnetic lines cutting the conductor increases the inductive reactance, and anything that decreases the number of magnetic lines cutting the conductor decreases the inductive reactance. Here's a conductor that's wound into a coil. It provides more inductive reactance than a straight conductor. As you can see, the magnetic field developed by one turn of wire in the coil cuts across almost every other turn as the magnetic field builds up and collapses. Since each turn of wire produces a magnetic field that cuts across the other turns, the inductive reactance of a coil in a circuit is proportional to the number of turns in the coil. The inductive reactance that a coil provides can also be increased by placing a metal core inside the coil. The metal core concentrates and directs the magnetic field that the coil produces. So, more magnetic lines cut across the conductor as current changes. So, coiling a conductor and adding a metal core are two ways to increase the inductive reactance in a circuit. Now, because inductive reactance limits current, when you change the inductive reactance, you are also changing the current. Increasing the inductive reactance decreases current, and decreasing the inductive reactance increases current. Okay, we've been looking at what inductive reactance does to current. Inductive reactance, as I've said, is a measure of the current limiting effects of inductance in a circuit. Now let's see what inductance does to the relationship between current and voltage. Remember the current and voltage sine waves we examined in the last segment? The circuit that went with those sine waves only contained resistance as a current limiting factor. The light bulb in the circuit provided resistance to current flow. Any inductance in the circuit was assumed to be so small that we didn't have to be concerned with it. Such a circuit is called a purely resistive circuit. The term purely resistive tells us that resistance is the only current limiting factor in the circuit. In a purely resistive circuit, when voltage increases, current also increases. When voltage decreases, current decreases. In other words, voltage and current stay together. When voltage and current stay together, that is, when they always increase and decrease in the same direction at the same instant, they're said to be in phase. Now let's look at a purely inductive circuit. That's a circuit in which inductance is the only factor that limits current. This symbol usually indicates a coil with high inductance. Actually, there's no such thing as a purely inductive circuit because every circuit contains some resistance. So this purely inductive circuit only exists in theory, but it's helpful in understanding the effects of inductance on the relationship between voltage and current. In this purely inductive circuit, when voltage starts to increase, current does not change right away. The counter EMF keeps the current from increasing immediately. Therefore, the increase in current takes place later than the increase in voltage. When voltage starts to decrease, the induced voltage opposes the decrease in current. So, the decrease in current takes place later than the decrease in voltage. Because the changes in current always take place later than the changes in voltage, it can be said that current lags behind voltage during the entire cycle. Whenever voltage and current increase and decrease at different times, they are said to be out of phase. In our purely inductive circuit, inductance causes voltage and current to be out of phase. In the next segment, we'll be talking about how capacitance affects the phase relationship between voltage and current. Before we start in on that, though, read through section 2 of your text. If you have any questions about inductance, be sure to clear them up with your instructor before we go on.